Good morning, everyone, and welcome to the 2014 edition of the Royal Tyrrell Museum Speaker Series. This is the third to the last presentation this year. Francois is unable to be here today, but the Royal Tyrrell Museum and its cooperating society are proud to present Dr. Alexandra Lefort. Alexandra is a research assistant at the University of Tennessee, Knoxville. Alexandra is originally from Vermelles in the north of France. She obtained a BSc from the Université d'Artois in Arras, France, before moving to Toulouse to pursue an MSc in Earth and Environmental Sciences at the University Paul Sabatier. For her thesis, Alexandra used data from lunar spacecrafts to create mineral and geochemical maps of the moon in order to reconstruct its geological history. After completing her thesis, Alexandra moved to Scotland to pursue a second MSc, this time in remote sensing at the University of Dundee. For her thesis, she used radar satellite images to identify zones of erosion and natural hazards on the Nazca archaeological site in Peru. Subsequently, Alexandra moved to Switzerland to pursue a PhD in planetary sciences at the University of Bern. For her dissertation, she used high-resolution imagery and energy balance modeling to investigate landforms occurring near glaciers on Mars, a study that she continued as a postdoctoral fellow at the same institution. Subsequently, Alexandra moved to the U.S. to hold a research assistant position at the University of Tennessee in Knoxville, where she began studying the fluvial networks and tectonic deformation found near the Mars equator. Alexandra's research interests focus on the formation and evolution of topography on Mars, particularly landforms shaped by the action of water, be it glaciers or rivers, and their potential for harboring life. Although specializing on Mars, Alexandra is also interested in the moons of the outer solar system, such as Titan, Europa, and Enceladus. Slightly closer to home, Alexandra is also involved in monitoring terrestrial environments using satellite data for conservation purposes and natural hazard assessment. Today, Alexandra will present an overview of her research about Mars, not on Mars, and its implication for the potential for life on that planet. Without further delay, I present Dr. Alexandra Lefort.
Thank you. Good morning, and thank you for coming. So, I'm going to talk about different evidence that we have for the presence of water on Mars, and also for the existence of landforms that are, or of environments that are favorable to the emergence of life on Mars, and discuss the implication for the possibility of life on Mars in the past and today. So why search for water? Well, the main scientific motivation for the exploration of Mars is the search for the evidence of life, whether it is past life or present life. And life, as we know it, carbon-based life requires water. So on Mars, the search for life starts with the search for environments that had habitable conditions, whether in the past or in the present. And habitable conditions include water. And in addition to having habitable conditions, we need environments that are also favorable to the preservation of fossils and organic materials. And the other interest of water is that it is a very valuable resource for potential future human missions on Mars. So currently, Mars is the equivalent of a very dry and cold polar desert. It has a very thin atmosphere, which is less than 1% of Earth's atmosphere. It's mostly composed of carbon dioxide. It's also a really cold planet. The daily mean temperature at the equator is minus 60 degrees Celsius, and it's about minus 120 degrees at the poles. And because it's so cold, not only water can freeze, but also carbon dioxide. So we find two types of ice. On Mars, we find water ice and carbon dioxide ice. So today, water on ice can only be can mostly be in a solid form, in form of ice, or in a gaseous form, and only in extremely exceptional circumstances we can find water as a liquid. It's it's located partially in the atmosphere, but really not much. There's only about 0.2% of less of water in the atmosphere of Mars. And most of it currently is located in the polar caps and in the subsurface in the form of underground ice. And with exceptions of the polar regions, water is unstable at the surface of Mars. So any water ice that will be present at the surface of Mars will sublimate in the atmosphere, which is the transition directly from an ice form to a gaseous form. However, we do observe a lot of landforms at the surface of Mars that suggest that the conditions must have been different in the past. So this is a topographic map of Mars. In red, we have the highest areas of Mars, and in blue, the lowest area. And what's particularly remarkable about the topography of Mars is what we call the dichotomy boundary, which is this topographic divide between the southern hemisphere and the northern hemisphere. The southern hemisphere is about 5 kilometers higher than the northern hemisphere, and it's much more rugged with a lot more crater, and it's also older. While in the northern lowlands, we have a much smoother terrain and much younger terrain. So this dichotomy was one of the reasons why we first thought that there may have been an ocean in the northern plains of Mars. We divide the Martian history in 3 major periods. So the oldest period is called the Noachian, and it lasted until about 3.7 billion years ago. At this time, Mars probably had a thicker atmosphere, which was mostly lost by the end of that period. And we know that it also had a lot of water. We can see signs of active erosion. A lot of craters in the older terrain of Mars are very eroded. We can see valley networks. We also know that it had lakes and maybe oceans. Then we have the Hesperian period, which lasted until about 3 billion years ago. This is a transition period from an active Mars with a lot of liquid water, with stable water at the surface, to the current Mars, which is much drier, less active, and where water is unstable at the surface. At this period, there was still sporadic water activity, especially catastrophic flows that created what we call the outflow channels. And Mars continued to lose its atmosphere during that period. And then we have the Amazonian, which is the current period, where Mars has a thin atmosphere, is a cold desert and with arid, dusty conditions. And although we have evidence of still occasional breaks out of liquid water, maybe triggered by impact, volcanism, or by the presence of salt in the water. So I'm going to talk about different lines of evidence that allow us to reconstruct the history of Mars, that allow us to tell what Mars was like in the past and where the water is now. And I'll discuss what this tells us about the possibility of life on Mars. So I'll start with the very early Mars from about 4.5 to 3 billion years ago, which covers the period of the Noachian and the Hesperian. And during that period, one of the most striking features that tells us that there was flowing water at the surface of Mars are those valley networks. The valley networks are located mostly in the southern island and in very old terrain. 84% of them are in terrains that are more than 3.7 billion years old. Although we do find some valley networks in younger terrains, which shows that there should have been flowing water in the surface even more recently. Those valleys are generally less than 5 kilometers wide and up to several thousands of kilometers in length. So valley networks show different morphologies, but most of them have morphology that's very similar to what we observe on Earth. So this is an example of a drainage network in South Yemen, which is pretty similar to what we observe on Mars. Those are dendritic valleys that are generally V-shaped with the first tributaries are generally narrower than the main channels. We see meandering channels, and they have a relatively high number of tributaries, although generally less tributaries than what we observe on Earth. And because of this morphology, we think that they probably formed the same way as most of the valley networks on Earth by precipitation and surface runoff. And this type of formation process requires that Mars had a thicker atmosphere and a warmer and wetter climate. We also observe that the valleys show different level of preservation. Some are more eroded than others, which suggests that they didn't all form at the same time, but they formed over a relatively long time and that there was multiple periods of formation. So if we look closer at some of these valleys, we see really neat fluvial features. This is an example of a really meandering channel on Mars, and which is pretty similar to what we observe here in Alaska. And the other feature that's interesting here was curvilinear ridges that we also observe inside of those meanders in Alaska. And those have been interpreted as scroll bars, which are vertical layers that result from the lateral deposition of sediments by the water inside of a meander. And what those meander and those scroll bars tell us is that this river must have been running for a really long period of time, because those only form in pretty mature fluvial channels. So we think that some of the valley network may have run for thousands or maybe up to several millions of years. If we look at the distribution of the valley network, we see that they are pretty much all located around the belt, along a belt that surrounds the planet, mostly south of the equator. So here all those little red dots represent valley networks. This distribution is both consistent with the formation by precipitation and with the presence of ocean in the lowland. We think that for a lot of those valley network, the water was flowing from the islands into the lowlands. And there may have been either one or possibly several oceans there. So at the end of several of those fluvial channels, we observe deltas. Deltas are those fan-shaped accumulations of sediment that form when a flowing water encounters a standing body of water and drops its load of sediments there. Those are very interesting because finding deltas tell us that there were standing bodies of water at the surface of Mars, so there was lakes and maybe oceans. And deltas are also environments that are conducive to the development of life and to its preservation, and to the preservation of fossils and organic materials. So those are really interesting places to investigate, to look for life on Mars. And this one, it's the Eberswalde Delta, which is the largest Martian delta, which is 115 kilometers square. And we think it may have formed over times of hundreds or thousands of years. So we can see here that the valleys that are connected to this delta, and this delta is located in the Eberswalde crater, and we think that there was in the past a lake inside of this crater in which this delta formed. So if we look closer at the morphology of this delta, we see that it's really close to deltas that we observe on Earth. We can see several lobes that indicate different episodes of deposition, and we can also see some meanders and even scroll bars. And what's particularly interesting about this particular delta, and we've observed that on other delta on Mars, it's the presence of clays. So this is a mineralogical map of this delta, and the red indicates the presence of clay minerals, while the blue indicates the presence of opal. So both minerals form in the presence of water, and those clay minerals are located mostly in the bottom layers of the fan, and we also observe some of it at the bottom of the crater. This location is similar to what we observe in terrestrial delta, where the clay settles out of the rivers into the deepest, the quietest part of the lakes and form those layers that we call the bottom set beds. And since clay, so we have here a configuration that's very similar to the delta that we have on Earth. And since clay is formed by the weathering of volcanic rocks over a long period of time, tens of thousands of years, and it forms in a water with a neutral pH, what this indicates is that there was standing body of water there for a pretty long period of time, and the fact that this was a neutral, that the water had a neutral pH makes it an habitable environment. So this is a very good environment where to look for potential life on Mars. And what's also interesting is that clay can form really well-preserved fossils, and delta are really good at burying and preserving organic materials and fossils. So if there were living organisms in this lake, it's possible that proof of the presence of those organisms, that organic material and fossils may still be preserved in the bottom set beds of this delta. So that represents the delta distribution on Mars, and most of the delta in blue are delta that form just like the Eberswalde delta in a crater, so that probably formed in crater lakes. And there are 17 deltas indicated here by those red squares that form just at the edge of the lowlands. And what's neat about those is that they're almost all at the same elevation. The fact that they're at the same elevation suggests that they may have all formed in the same body of water, and this body of water may have been possibly a large northern ocean. And in addition, the location and the elevation of this delta is also consistent with the location and the elevation where we find the fluvial channels. The other major fluvial features that appear to have, where water appears to have flown into the lowlands are what we call the outflow channels. Those are really different from the valley networks. They are huge. They're more than 100 kilometers wide, several thousands of kilometers long, and they can be up to 2.5 kilometers deep. They originate in this type of collapsed terrain, and we think they form by catastrophic flood, when water ice that was preserved in the surface melted due probably to volcanic activity and burst through the surface, causing this collapsed terrain and forming the giant outflow channels. And this occurred over a pretty long period of time. The major outflow channel formed by the early Hesperian, which was about 3.7 billion years ago, but we have evidence of formation of outflow channel until the Amazonian, so in the relatively recent past. And what's particular about those outflow channels is that they do not require rainfall to form, so they could have formed in climatic conditions that are really similar to what we have now on Mars. And if we look at the map of the distribution of the outflow channels, they are represented here in red. We see that they are located also at the border between the lowlands and the highlands. So those outflow channels may also have contributed to a northern ocean. So I've talked until now about the evidence that we have of flowing water at the surface of Mars in the past, but we also have some evidence of the possibility of underground water, and in particular hydrothermal system. This is a 3D model of a volcanic cone that's dated from about 3.7 billion years. And what's really interesting here was white deposits, and this is a close-up of one of those deposits. Those are silica deposits, and silica deposits form when groundwater is heated by magma and cause dissolution of the mafic minerals and creates fluids that are really saturated in silica. Those silica are brought to the surface by vents and hot springs, exactly like what we have in Yellowstone, for example. And they are deposited at the surface, and this is probably what we are seeing here. So on Earth, this type of environment is really favorable to the development of microbial life, and it's also an environment that's really conducive to the preservation of fossils. So here we have, again, another type of environment on Mars where we could potentially find evidence for life. I've been talking until now about observations that we've done from orbits using the orbiting spacecraft. So I'm going to talk a bit about the results that we obtained from the different rovers at the surface of Mars. And I'm going to talk here about the results from Opportunity and Curiosity. And what the rover found in general confirmed the observations that we've done from the spacecraft. I'll start with Opportunity, which is located here in Meridiani Planum. Opportunity has explored terrains of different ages, and the most interesting discovery was made in the older terrains, which were dated to about 4 billion years old. And this is an area on the hill that is called Cape York, and what Opportunity found here, and especially in those two locations, are again clays that are located in fine-grained layered rocks. And it also found associated with this clay calcium sulfate vein, which are features that all form in the presence of water. And not just any water, in water that's only slightly acidic or that has a neutral pH. So again, we have here a very old environment that had water, that had favorable conditions for life, and it was really favorable for the prebiotic chemistry and the appearance and development of microorganisms. In later terrains, the conditions are not so good anymore for life. This is a view of Eagle Crater, where Opportunity found no more clays but sulfate-rich sediments. And so those are two of the major discoveries of Opportunity in this area. The first thing that Opportunity found are those blueberries. Those are composed of hematite, which is an iron-rich mineral, and which form when the rock is really saturated with water and the iron precipitates out of the rock. And those are extremely abundant in Eagle Crater, and they are indicative of the presence of a very wet environment. Next to those blueberries, we observe this type of rock, which is even more interesting because it contains sulfate salts, such as, for example, Jarosite, which is an iron sulfate mineral, which only forms in very acidic water. So we think that what happened there are episodic flows of shallow water followed by evaporation, desiccation. There may have been some ponding of really acidic water with extreme salinity. This would have been a really difficult environment for life, but we do find some environment on Earth that have similar conditions. For example, this is an image of a Rio Tinto in southwestern Spain, and it's also an environment extremely acidic, extremely salty, but in which microbial communities actually thrive. So this environment may be a possible analog to the environment of Eagle Crater in about 3.7 billion years ago. So let's see now what Curiosity has found in the Gale Crater. Gale Crater is located here, and it's a really interesting location. It's this 150-kilometer wide crater that contains this mount that has been dubbed Aeolis Mount or Mount Sharp, that's about 5.5 kilometer high, and it's made of this stacking of sedimentary layer. And we think that most of those layers are sediments that settled down on the bottom of a lake that was filling this crater sometime in the past. The age of this mount is those layers have been deposited over about 1 billion years of time. So the lower layer are dated to 3.8 billion years, and the top layer are dated to about 2.8 billion years. So what we have here recorded in this layer is 1 billion years of Mars history. And one of the reasons why we sent Curiosity there is that we did a lot of, we observed this crater, we studied it a lot from orbit, and we found a really interesting and very diverse mineralogy. This is a mineral map where each of the colors represent different minerals. This area represents the lower, older layers of the mount, and those areas represent the highest and the youngest layers of the mount. what was found in the lower layer and in a large part of the mount are different types of clays. And as we arrive closer to the top, those clays are mixed with sulfates, and at the top of the mount, we only find sulfates. So what this represents, it's a global shift from a warmer environment with water with a neutral pH that was more favorable to life to progressively a colder and more acidic environment, less and less favorable for life. So what we have in this crater, it's basically a record of climate change on Mars. So for now, Curiosity is exploring the lowest, oldest area of the crater, which are dated from around 3.7 billion years. And what it found here in this area, which is called Yellowknife Bay, it's again a clay-rich and habitable environment. And the first, actually what it found really, it's a full system of fluvial and a lacustrine system, fluvial streams and lakes, and possibly also underwater system, groundwater system, sorry. The first evidence for the fluvial environment was those sedimentary conglomerates, which are large rounded pebbles that are cemented together by the action of water. And so those are really similar to what we find on Earth, to the type of gravel that we find on Earth at the bottom of streams. And those gravels suggest, well, the shape and the size of those gravels suggest that they've been transported and abrased by a pretty vigorous and sustained water flow. And by studying the size, the shape, the distribution of those pebbles, it's possible to measure, to estimate the speed of the water, which was probably about 1 meter per second, which is equivalent to walking pace. And the depth must have varied from ankle deep to about hip deep. Very, very close to where those gravels have been found, Curiosity drilled a first hole and analyzed the powder that was taken out of this hole. And what Curiosity found are clay-rich, fine-grained mudstones, and that have been dubbed shipbed mudstones. So what those clays show again is that there must have been there abundant liquid that could soak the soils long enough to allow for the clays to form. And the other analyses also show that this area had a very low salt concentration, and the subsurface, the older terrain, are less oxidized than the surface. So we can see here that they are gray instead of the surface that's really oxidized and is red. So if we had been standing in Gale crater at that time, what we probably would have seen are streams flowing down the crater walls and being distributed into a fan into a lake that was spawning at the bottom of the crater. This gray mass had the neutral, only slightly salty conditions. Again, an environment that was favorable to life and to the preservation of organic materials and fossils. The other interesting observations is that we observe very little weathering or erosion of the crater rim, and this suggests that there was very little rainfall at the time. So this was an habitable environment, but the climate at that time was already relatively cold and dry. To summarize those discoveries by Curiosity and Opportunity, so we can tell that in the oldest period, the Noachian, we find mostly environments with clays, which are indicative of an environment with a neutral pH that was wet probably for a relatively long period of time, and that was really favorable to the development of life. As we move along in time during the Hesperian, we find more and more sulfates, which are indicative of a much drier and acidic environment and probably much more episodic flows. So a less habitable environment, but where some of the extremophiles that we find on Earth could possibly have thrived. And well, finally, we get to the present, and where we find mostly anhydrous ferric oxides and environments that are really arid and frozen and much less or not at all habitable. So 4 billion years ago, Mars may very well have looked like this, with large northern oceans, several lakes, channel systems, some streams, underground water, hydrothermal activity, with a thicker atmosphere, and those are conditions where life could have very well appeared and developed. And as the atmosphere got thinner, the conditions started to degrade, and we find more acidic environments, and then we arrived to Mars now, which is a cold and dry equivalent of a polar desert. If we add all that water on Mars, where did that water go? So we know that part of it was lost to space. The rest, some of it was locked in, condensated and was locked into the polar caps, and a lot of ice was preserved into the subsurface. So we have several ground ice reservoirs on Mars. So if we look at the polar cap, those are the only places that have uncovered ice in pretty significant quantity. They are about 3 kilometers thick, and the particularity of the southern polar cap is that it's not just water ice. It has a layer of carbon dioxide ice that's about 8 meters thick on top of a layer of water ice. We observe seasonal variations in the poles. During winter, there is deposition of carbon dioxide ice, which then sublimate again in summer. And the caps themselves are not the only place in the poles where we find water. Around the polar caps, above polar caps, we find thick deposits that have a diameter of about 1,000 kilometers and the depth up to 3 kilometers. Those deposits are formed by this alternance of dark and brighter layers, and those are layers of dust and ice, and this is a radar cross-section of those deposits. And we can, so the radar could actually see under the surface, and we can see the internal structure of those deposits, and we see really well this alternance of dark and bright layers. And those represents an alternance of icy and ice-free deposition, icy and ice-free climatic cycles in the relatively recent past of Mars. We also know that there is ground ice on Mars today. So this ground ice takes the form of a mixture of ice and dust that's located in the subsurface under an ice-free layer. The depth of this icy layer increases from the poles toward the equator. So at the pole, the icy layer is really close to the surface, and as we go closer to the equator, the depth of the icy layer increases, and it is probably about 1 meter deep or more at around 40-degree latitude. So this was originally a model based on the stability of ice on Mars, and this has been confirmed by observations from spacecraft and then by landers observation. For example, this is a map acquired by remote sensing of the percentage of water on Mars at a depth of about 1 meter. So this represents the amount of water in the first 1 meter of the surface. And what we see here, so the blue areas are the areas where there's the blue and the purple area are the area with a relatively significant percentage of ice, water is mostly in the form of ice. So we think that this represents water ice in the surface. And those areas have a percentage of 7% and up to 70% at the poles, while the central part, the equatorial part, only have between, at best, 2 to 7% of water. So we see a decrease in the abundance of water in the top first meter of the surface as we go toward the equator. And we think that there may still be ice in the subsurface at the equator, but this ice, to be stable, will have to be buried under several hundreds of meters of ice-free material. The presence of the ground ice has been confirmed directly on the ground thanks to the Phoenix lander. Phoenix landed at 69-degree latitude here. And all what Phoenix needed to do to find ice was to dig a trench of just a few centimeters deep into the soil, and immediately we found this deposit of ice. So so this confirmed this configuration that at the high latitude where ice is really close to the surface. And this was pretty neat because Phoenix was the first spacecraft that actually could directly touch ice on Mars. We can also see directly ice at mid-latitude, so more in this area around 30-40 degree latitude where ice is much deeper into the subsurface by looking at really recent, really fresh craters. And a lot of those really fresh craters at high and mid-latitude have deposits of ice at the bottom or around their rim. And what happened there is we think that the impactor penetrated through the surface, through the ice-free layer, and excavated the ice. Some of this ice was probably vaporized and then recondensated around the crater, forming those white deposits. And this is not observed in equatorial regions, so this confirms that the idea that there is no ice at least not in the shallow subsurface in equatorial regions. And if we look at images of this crater that have been acquired over the time of several months, here from October to January, we see that those deposits are slowly disappearing. That's because once the ice has been excavated from the subsurface, it's not stable anymore, and it sublimates into the atmosphere. Another evidence of the presence of ground ice at the mid-latitude are those gullies. Those are really small and incised channels that form only on steep slopes, such as crater walls or dunes. They start with alcoves, and then there's a couple of very fine channels, and then they end up in general by a depositional fan. We also observe some meandering and some braided channels, which are really typical of a formation by the flow of a liquid. So we're not sure exactly how they form, but some of the major hypotheses are that they form by either melting of ground ice of snowpacks, and we have an analog for that on Earth in the dry valleys in Antarctica, where we find this type of gullies which form by episodic melting of ground ice. Another possibility is that those gullies form because of flow out of aquifers, and in this case the ground ice will melt because of geothermal events, volcanic activity, and this water will be flowing horizontally in the porous rocks, such as, for example, sandstone, and breach out of the crater wall. And we are not sure in which case is which is the right mechanism for formation of those gullies, but if they are actually aquifer, this is particularly interesting because that will mean that there was water and liquid water in the underground in the recent past, and potentially environments where life could have developed. And we also observe at the mid-latitude, especially around 30-45 degrees latitude, this type of flow features that are called low-bade debris operons. And we know, especially due to radar data that have been able to image through the surface and see under those deposits of rocks and dust, we know that those contain very large amount of almost pure water ice. And this pure water ice is protected from sublimation by a few meters of rocks and dust that are deposited on the surface. In that sense, they are really similar to other flow features that we find on Earth that are rock glaciers. And the fact that this ice is really close to the surface it's really good for future human exploration, because that means it will be really easily accessible. So here, this is an example of one of those flow features that flows from this top crater into this secondary crater and then into a larger crater here. This is what we actually see on images of Mars, and this is what this would look like if we remove this layer of rock and dust. So we think that those features formed relatively recently, but under different climatic conditions. that they form when, just like terrestrial glacier, when snow and ice accumulated at altitude by precipitations and formed glaciers along the slopes, and that debris that were eroded from nearby steep slopes covered those glaciers, and once the ice was covered by a relatively thick layers of rock and dust, it was protected from sublimation, which is why we still see this ice under the surface right now. And we not only find glaciers at the mid-latitude, but we also find them really close to the equator. We have found this type of glacier at the base of some of the major volcanoes on Mars, which is Olympus Mons and the three Tharsis volcanoes. And this is an example of a glacier that we find at the base of Olympus Mons. We also think that those formed by deposits of snow and ice at higher altitude than those volcanoes, and what we see are leftover of larger, more extensive glaciers. And those are also relatively recent. They formed probably between about only a few hundred million years to about 4 million years ago. And what this shows is that there was, at least at altitude, a lot of surface at the equator of Mars in the relatively recent past. So how do we explain those landforms in the presence of ground ice at mid-latitude and at the equator? Well, we think that this ice had been emplaced there during what we can call Martian ice ages. And we think that those ice ages were triggered by tilt of the axis of rotation of Mars, which is called the obliquity. So on Earth, the axis of rotation is really stable because the Moon has a stabilizing effect, but on Mars it varies a lot. Currently, it is pretty similar to the tilt of the Earth axis. It's around 25 degrees, but we know that in the past million years, the tilt has varied from 15 degrees to up to 45 degrees, and it went even up to 60 degrees in further away in the past. And this oblicity, this change of the tilt of the axis of Mars, the periodicity of this change is only about 120,000 Earth years. So what we think happened is, if we start with a situation with Mars is at low obliquity, around 15 degrees obliquity, at this time the sunlight mostly hit directly the equator, which causes any ice that's located here to be vaporized and to be redeposited in the polar caps. So we have a situation where the surface at the mid-latitude and equator is really dry, and we have really large polar caps, and most of Mars is really completely free of ice. Then, as the planet tilted to a higher obliquity, more than 35 degrees, what happens is that the sunlight hit mostly the polar region of the higher latitude because the poles are more directly tilted toward the sun. So what happens there is, since there's more sunlight on the pole, the polar ice sublimates, and the sublimation of ice in the atmosphere increases the humidity of the atmosphere, which causes the ice to be stable at the surface, not only at the poles, but also at the lower latitudes on Mars. Because sublimation also creates pretty strong wind that cause water and dust to be transported by the wind to the lower latitude. And then this water that's mixed with dust condenses and accumulates at the lower latitude. And we have a situation where Mars is mostly covered by this relatively thick mantle of ice mixed with dust. And as the ice accumulates at higher latitude, we also have formation of glaciers. So we're in configuration here where most of the lower and mid-latitude consist of a dry layer, which is covered by a significant amount of ice mixed with dust. So in that case, we have Mars in what we can call a glacial period. And so we think that this type of configuration probably happened between 5.5 and about 10 million years ago. And as the planet goes back to a lower obliquity, and then we are in the situation where Mars is currently, As it returns to low obliquity, the sunlight hits again mostly directly the equator, which causes again ice to vaporize at the equator and mid-latitude and recondenses at the pole. So the fact that ice sublimates at the mid-latitude causes this degradation of this mantle of ice and dust, and as more of ice is removed from that mantle, the fraction of dust in the mantle increases, and we arrive at the situation where there is a pretty thick layer of dust in the mid-latitude, and this layer of dust covers whatever is remaining of ice that has not sublimated yet, and protect the remaining ice from sublimation. So we're in a situation where we have a layer of ice between two dry layers of dust, and this thick layer of dust here stops the sublimation of the ice, which is why we still have ice in the mid-latitude today, and which is because of this ice that we have formation of the gullies of a glacier, and that we can see this ice directly at the bottom of craters. And so we can say that currently Mars is in an interglacial period. So we know that ground ice is stable in Mars, at least under a protective layer of dry soil, but we were not expecting to find flowing features on Mars at present, since water is not supposed to it can normally, in the current condition, not take a liquid form at the surface. However, we did find in the past couple of years some features that seem to have been formed by very recent flows, and those have been called the recurring slope lineaes, and these are those funnel depressions that are less than 5 meters wide and up to about 1,000 meters long, so they are much smaller than the gullies. We observe them on steep slopes at the mid-latitude and at the equator, and we can see changes with the season. So they appear and flow in spring and summer, for example here. So we see this dark marking that represent flow during the summer, and in winter they fade away again, and then they reappear at the next spring and summer. And we don't really know. We're not sure how they form, but we think that the most likely scenario is that those form by flow of salty water, because the dissolved salt in the water will keep the water liquid at temperature where pure water will freeze, and also the presence of salt will slow the evaporation rate, so that will allow this feature to flow further down the slopes. And we don't find many of them. The last studies that investigated those features investigated 200 sites and only found 13 sites that had those features. So that probably means that they need some really specific conditions to form. They probably need a particular combination of availability of water and salt, and maybe steepness of salt and type of exposure to the sun. So this is. We're still investigating those. It's a really recent discovery, but it's really interesting because if there is liquid water under the surface today and even salty water, there may be still now pockets of water under the surface that, even if it's salty water, which could be potential habitats for microbial life and for extremophiles. So in summary, we do know that there was really abundant liquid water on early Mars, at least episodically. We have evidence of habitable environments up to about 3 billion years ago, environments that were more habitable around 4 and 3.8 billion years, but some environments even more acidic that would still have been habitable for some particular type of microorganism. So it is possible that life arose on Mars during those early times of the planet history. And today, Mars is, at least on the surface, is dry and cold, and the conditions are really not favorable to life. However, we know there's still water in abundance on the planet. We know there's water in the polar caps, there is subsurface ice. There may still be today hydrothermal activity. and we observe occasional surface flows. So this is purely speculative, and we don't have any evidence for it, but it's not impossible that there may be underground pockets of liquid water still now in Mars, and that life may have developed in those locations. So what's the future of the search for life on Mars? Well, it's really challenging to find evidence for the existence of microbial life that arose billions of years ago and on a planet that about 225 million kilometers away. However, it's not impossible, and just to give an idea of how complicated this is, for example, if we want to detect organic molecules, we need first to find a site that was primarily enriched in those organic molecules. And then those organics must have been preserved during the transformation of the sediment to rock. And finally, this rock must have been preserved from the solar radiation that will destroy the organic material. And those radiation can penetrate up to a top few meters of the subsurface. So the best place to look for life are rocks that have been buried really deeply, protected from those radiation, and only exhumed really recently. And fortunately, we can measure the time since exhumation, and Curiosity has been doing that in Gale crater. So the next goal for Curiosity and the future missions will be, in addition to looking for more habitable environment, will be to find material and locations that were conducive of the preservation of organic materials, of fossils. And in that sense, what we're doing on Mars, it's pretty close to the discipline of taphonomy in paleontology, which is to understand the preservation process of biological material. So Curiosity and Opportunity are not built to look directly for signs of life, but there will be, at least in the near future, 2 future rovers that will be exactly designed for that. And this is ExoMars, which is a ESA mission, which will start in 2016 with an orbiter, and then in 2018 with a rover. And the landing site has not been decided yet. And then there will be a NASA mission, which is called, for now, Mars 2012, which is still in preparation. So we may very well know in the next maybe 10 years whether there was actually life on Mars or not. And that's it. Thank you.